Hello Chem1B, this is our solution chapter video 6, and in this video we're going to be talking about colligative properties. Now what is a colligative property? Colligative properties are properties of a solution that depend not on the identity of the solute that we're adding, but instead how much of the solute was present. So if you add one solute or a different solute, that doesn't matter. It matters that the concentration has been changed, how many particles of solute are present, not which one you dissolved. There are 4 colligative properties that we'll be covering in this unit or in this chapter, and they are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. All of these change not by the identity of the solute we've added to the solution, but instead based on the concentration of solute particles in the solution. Now, in this video, we'll start discussing vapor pressure lowering. This is our longest colligative property to discuss, so this will span 2 of our videos, and then in later videos, we'll discuss the rest of these.
Vapor pressure is an equilibrium system where we have the rate of evaporation and the rate of condensation being equal, like we talked about in chapter 11. However, when you add a solute to the system, what happens is that some of those solute particles are going to be on the surface of the liquid, and that is where the evaporation occurs. So adding a solute lowers the rate of evaporation of our solvent, the blue liquid in this picture. This creates a scenario where fewer solvent molecules evaporate, making more of these guys condense. As more of these condense, eventually these rates will become equal again. And we get to a lower rate of evaporation equal to a lower rate of condensation. But at the end of the day, what the result is less particles in the gaseous state above the liquid. So our vapor pressure goes down. Vapor pressure of a pure substance drops whenever we add a solute, therefore. And we have an equation for this. It's called Raoult's law. Raoult's law looks a lot like Dalton's law, and it's similar but not the same, so be very careful with those 2 equations. In Raoult's law, we have the vapor pressure of the solvent over the solution. I should say, or the volatile component. So it could be the solvent or the solute if both are volatile, i.e. have a high rate of evaporation, therefore a big vapor pressure, or a significant vapor pressure, then we have to take into account both. The x1 in the equation is our mole fraction of the volatile component. The solvent most of the time is the thing that's volatile, but like I said, could also be the solute. And P naught 1, that's the naught, is the vapor pressure of the pure solvent if it was by itself, no solute present. As the purity of our solvent decreases, so too does the mole fraction, and therefore so does the vapor pressure of the solution. The total vapor pressure in the solution depends on whether both the solvent or the solute are both volatile, or if only one of them is volatile. If only one of them is volatile, the vapor pressure of that volatile substance is equal to the vapor pressure of the solution. If both are volatile, it's the sum of the 2 vapor pressures. So let's look at a problem involving just one volatile component, and that volatile component is water. And we'll talk about how we know water is the volatile component in this problem because it's not explicitly stated. We're told that what is the vapor pressure of a 35% by mass aqueous solution of ethylene glycol? And this is the formula of ethylene glycol. At 20 degrees Celsius. The 20 degrees Celsius isn't really important. It's just, hey, we're calculating all this at that temperature. We're told that the vapor pressure of pure water is 17.5 torr. And it's this number here, the pure vapor pressure of water, that gives us a clue that water is our volatile component, while ethylene glycol is not. We do not have a pure vapor pressure for ethylene glycol, which leads us to assume that it does not have a significant vapor pressure. So we have our equation P1, which in this case is going to be H2O because it's the volatile component, is equal to the mole fraction of water in the system times the pure vapor pressure of water. And this is 17.5 torr. What I need to solve then is my mole fraction of water, which we know is equal to the moles of water in the system divided by the total moles. Now, in order to get these two, I need to do some conversion because I know the solution is 35% by mass ethylene glycol. So I'm going to make the assumption that I have 100 grams of solution. And if I do that, that tells me that I have 35 grams of C2H6O2 ethylene glycol. I can calculate its molar mass and get moles of ethylene glycol. And this will get me the molar mass of ethylene glycol is pretty much 62.08 grams per 1 mole of C2H6O2. That's important. I need that value. And if I do that calculation, I get about 0.564 moles of C2H6O2. I also need the moles of water. So I need the grams of water. And water is my solvent. So if I have 35 grams of this, then I have 65 grams of water in the system because the total mass of the system is 100 grams. And 100 minus 35 is 65 grams. We know the molar mass of water is 18.02 grams per 1 mole. Or we can calculate that. And so this gets me that I have 3.61 moles of water present in the system. And therefore, in other words, my mole fraction of water is equal to 3.61 moles of water in my numerator divided by 3.61 moles plus 0.564 moles. And that mole fraction of water, therefore, is equal to 0.865. And therefore, my vapor pressure of water is going to be equal to 0.865 times 17.5 torr, which gives me 15.1 torr as the vapor pressure of the solution. All right, so if you have any questions, just let me know in office hours or my email.